So we're starting this lightning session now. To kick us off is Jan Feld talking about how to find phenomena in myths.
Cool, thank you. So I'm Jan. I'm an economist, and I've been wondering how we should find phenomena in the midst of the replication crisis. So I've been doing some reading in philosophy of science and came across the concept of phenomena, which I find very useful, is a relatively stable and general feature of the world. So as an example, a potential phenomenon might be that women are generally more risk averse. And so I underscore generally to mean that it's not only something that applies to one specific example or one specific country, but maybe it's something we should expect to be generally true, or it might not be true, but the question is kind of how do we really find out if that's the case. And so one approach might be to conduct a literature review or find a literature review. And so those literature reviews often have tables that then summarize all the results, and I kind of made one up here. And I see a few problems with this approach. So, for example, the included studies might be relying on selected samples. So maybe there's samples from just Western countries or just students, and it's not obvious how these results generalize. In the second column, I have my hypothetical results. And you can see that the first three results, first three studies show that women are more risk averse. But then study 4 shows that men are more risk averse. And it's not obvious whether that's a real effect or maybe that's just sampling error. Maybe it's just due to chance because you summarize many studies. One is by chance found to find something else. And then the last 3 studies show results that are not statistically significant. It's not obvious whether that means that there's no difference or whether they would have found a significant difference if they would have had a larger sample. And then across all of this, we have the problem of publication bias. So somebody went to the trouble of summarizing all 7 studies they found, or maybe the studies in the best journal, but what about all the other studies? Or what about the studies that didn't get published? Now, then I thought, okay, so what about meta-analyses? So meta-analyses summarize all the existing estimates in the literature. And so the nice thing about them is they can correct for sampling error and then estimate the distribution of the latent, of the unobserved effect. So basically you take all the estimates you find, then apply some statistical model like the random effects model, and then you're left with the distribution of the true effect, which might vary, but also this way you've explicitly cancelled out sampling error. Now, the problem I see here is bad input. So the methods, I think, are great, but if we're concerned about the quality of the original studies in the literature, let's say we're concerned about p-hacking and publication bias and selected sample, then that's what I call the garbage in, garbage out problem, right? If you feed this great methods bad input, then kind of taking an average of the bad studies, it's not going to do the trick. And there's some evidence that correcting for publication bias after the fact is actually really difficult and often does not work. So the solution that I propose is to get estimates from many contexts, so to take care of the selected sample problem, that have not been filtered through the publication process. Then estimate your parameter of interest for each context, so the thing you're interested in, and then use meta-analysis methods, because I think the methods are great, to estimate the unobserved distribution of the true effect to explicitly account for sampling error, and then repeat this process many times with different methodologies. Now, I can summarize this with what I'm proposing is meta-analysis with quality-controlled estimates, quality-controlled inputs, so making sure there's no publication bias, all the estimates, you know what went into them, they're comparable, and triangulation. Now, you might be thinking, wow, that sounds like a lot of work. And you're right, it often is, but for an important question, I think it might be worth it, and we might need to team up, do some big team research. However, if you're lucky, you might find existing data sets like multi-country surveys that allow you to do that. And for the research question, if women are generally more risk averse, I've been lucky to find lots of data that actually allows me to answer this research question. So there's a world map in gray, you see the countries for which I have data. And so I have 13 different measures of risk aversion from 114 different countries. And if you're interested in hearing about the preliminary results, I talk to you after the presentation. Cool, thank you.
So the next talk is online. We have Linnea Gandhi.
Hi, can you hear me all right? Great. All right, it's nice to see everybody virtually. I'm sorry that I can't be there in person. My name is Linnea Gandhi, and I'm a fourth-year PhD student at Wharton. The work that I'm presenting today is jointly done with my advisor, Duncan Watts, as part of the Computational Social Science Lab. We also have a huge team behind the scenes who I would love to thank up front. So the problem that I'd like to share is that in my field of behavioral science, nudging, beyond the replication crisis, we've had a lot of issues with people just wondering whether nudges or psychologically informed interventions work at all. People are asking, do nudges work? This is something that I asked after spending about a decade in practice prior to coming to academia. And I think there's a couple of roadblocks that prevent us from even being able to answer this question at all today. One of them is generalizability. We run a study in America. It's really hard to know if it's going to work in a new context like Australia. Even if we knew, though, which parameters mattered for generalizability, we have a second roadblock, which is transparency. Not all papers document all parameters, such as demographics. But even if they did, we'd have a third roadblock, which is commensurability, or the toothbrush problem that we just heard about. In my field, there are lots of concepts that sound similar, but actually mean different things, such as the word simplify. Simplify for this Muncher framework means something very different than in the Bashir's framework, or Della Vigna framework. So it's a mess. It's really hard to fit all of this literature together. I think the root cause around all of this is that we're asking too much from our papers. We're trying to get them to share and store knowledge at the same time. And to maximize these two activities, you actually have to follow different strategies. So sharing knowledge requires summarizing, abstracting, persuading. Storing knowledge requires pretty much the opposite, giving me all the granular detail that I want, organized according to knowledge frameworks that I already have, not novelty, but kind of boringness. And what we're trying to do in the lab is to take a lot of the knowledge that is caught all over different papers and pull them into a single database of cumulative evidence. We've got a big process behind the scenes that I won't go into detail right now on because we have very limited time, but we're trying to do something beyond meta-analysis, beyond systematic review, where we're using LLMs, manual coding, author review to continuously accumulate evidence across practitioners and academics, and even run new RCTs to fill in gaps in this database over time so we can start to answer really important questions like, do nudges work? We've done this for about a year and a half. We've coded over 150 experiments of over about 400 parameters to try to answer those generalizability questions. And we're starting to do the really fun work now, which is analysis. So we can start to find areas of the space that are empty where we really need new evidence, such as in developing countries. We can also start to translate and actually address commensurability issues. So we're addressing 56 different nudge concepts across the literature and coding every single treatment condition across them. So we can start to see how similar are two of these phrases and these concepts that authors use. The more experiments that share those concepts in tandem, the more similar they are. And then we can start to do things like cluster analyses. I know this is really small, but I'll show you here. We can start to empirically say how commensurable or how much different toothbrushes are the same or not. So this is the simplification idea I showed earlier. I can actually show you how different they are and how their definitions differ empirically because of this cumulative database. And then finally, we can explain to build new theories and predict out of sample whether a nudge is going to work from one context to the next. You can run a lot of different models to do this. We're doing random forests right now with a pretty good R-squared. And we can start to look under the hood to see, using permutation importance plots, which of the variables, which of the parameters are actually really important for prediction. So going into the black box, and we're finding things like whether something is feedback involved tends to correlate well with effect size and has predictive validity. And the longer a behavioral measure is, the longer it takes, the lower the effect size tends to be. All things that are kind of common sense, but we're starting to actually be able to do this using empirical data. I know I'm probably running out of time, so I'm just going to end with a provocative question. How can we know what we know as a field, whether it's behavioral science or any social science, if we don't have computationally cumulative evidence? I don't think we can. And I think a root cause is that the way we produce scientific knowledge today, again, at least in social science, is flawed. Papers are really good at sharing. They're not very good at storing. We need to move more towards cumulative database and maps to know what we know. And with that, I'm looking forward to talking after the break.
Right, if you guys can hear me okay. Hello, I'm Bill. I'm a medical student from Western Sydney University, and I'll be presenting our project on the quality of recently published studies in pediatric surgery, which may possibly be the most challenging subspecialty in which to conduct research. Barriers include, but not limited to, ethical concerns over long-term complications and recruitment challenges for diseases that are often rare and heterogeneous in nature. Although the physical and physiological differences of a child to an adult means that dedicated research is required, there has been few randomized controlled trials for the population. For example, only about 2% of all studies published in this field in 2013 were RCTs. Consequently, only up to 11% of interventions used in practice may be supported by RCT-derived evidence. Risk of bias refers to the extent to which estimated effects in a study is distorted by systematic errors in its design or conduct. This has never been determined for RCTs in pediatric surgery. Reporting quality refers to the extent to which a study provides a complete and accurate account of its design and conduct. This has not been assessed for systematic reviews and meta-analysis that includes these RCTs in over 2 decades. Clearly, a knowledge gap exists, which we aim to address by determining the risk of bias and reporting quality of recent RCTs, systematic reviews, and meta-analysis. To do so, we conducted a cross-sectional study in pediatric surgery as indexed across 6 databases and 4 high-impact journals. 6,757 articles were identified for screening, and pertinent inclusion criteria as per our prospectively registered protocol were: more than half of the study participants had to be 18 years or younger, the intervention had to be invasive and used intraoperatively, and the studies had to be published as full text in 2021. Our work was strengthened by the inclusion of articles written in languages other than English, and article screening was done in duplicate by 2 independent investigators who utilized ROB2 and Console for RCT, and Robust and Prisma for systematic reviews or meta-analysis to determine the risk of bias and reporting quality respectively. Overall, risk of bias was assessed as low, unclear, or high, while reporting quality was assessed as adequate if 75% or more of items in the relevant guidelines were reported. Our findings were validated against existing assessments in the literature, and the association between identified quality and study characteristics were explored using stepwise regression. So a total of 371 articles were included in our review, making it the largest review of reporting quality and risk of bias in RCT in pediatric surgery to date. We found that only 1 RCT and 4 systematic reviews and meta-analysis were adequately reported. More than half of RCTs and nearly all systematic reviews and meta-analysis were at high risk of bias. And less than half of RCTs and just over a quarter of systematic reviews and meta-analysis had a registered protocol. So why has the proportion of studies with poor research quality remained elevated, and what are possible strategies to address the issue and increase the quality of synthesized evidence? We suspect the lack of predefined protocol may be due to limited enforcements by journals during peer review. However, this was one of the most significant predictors of reporting quality for both types of research. It was also associated with a low risk of bias in systematic reviews and meta-analysis. To enhance transparency and reduce selection and observer bias, or even post hoc adjustments, it may be prudent to implement stricter reporting requirements for trial registration status. A higher number of authors were associated with low risk of bias in RCTs. Intra and interdisciplinary collaboration, such as with methodologists, may address deficiencies in study design, data analysis, and reporting. Therefore, as a part of research grant allocation, it may be prudent to consider the proposed number of authors, their qualifications, and their expertise. Surprisingly, 162 or 56% systematic reviews and meta-analysis do not have a risk of bias assessment, which is a critical step, and its absence seriously undermines the utility of these published findings. Authors should evaluate the risk of bias, and journals should enforce stricter submission requirements. In conclusion, the risk of bias and reporting quality in pediatric surgery has not improved over the past 2 decades. Thank you.
Hi everyone, my name is Adam, and today I'll be sharing some insights from our investigation into the quality of systematic reviews and meta-analyses in dermatology, which is the study of skin disorders, and specifically looking at how it has changed over the period of 10 years.
Click. So it's one because it's clicked.
That's great.
Just hold on for a second. Just don't touch it there for a second. Still clicked on that. Sorry.
Oh, that's great. All right, so starting again, we're just going to look at the quality of systematic reviews and meta-analyses in dermatology. So systematic reviews and meta-analyses are often regarded to be a very high tier of evidence and a source of high quality information based on which we make clinical decisions as well as write healthcare policies. And we've noticed that over the last few years, more and more have been published each year at an exponential rate. However, the quality or how well performed these systematic reviews and meta-analyses are is under question. So in other fields of medicine like hepatology, cardiology, and orthopedics, they found sort of conflicting conclusions or results, and some have attributed this to the varying levels of quality of conduct of these studies. So this slide just illustrates the rate at which these study types have grown in recent years, with one study even finding a 2,728% increase in published systematic reviews between 1991 and 2014. So we wanted to determine if, in the field of dermatology, the passage of time over the span of a decade had affected the quality of systematic reviews and meta-analyses, specifically how at risk of bias they were and how methodologically sound they were. And this was our primary objective. And we also wanted to find out if the reporting quality of these systematic reviews and meta-analyses had improved over time, and this was our secondary objective. And to achieve these objectives, we performed electronic database searching of 10 databases, specifically including studies that were published in the 10 highest ranking peer-reviewed dermatology journals as per Generalize, and we included them if they were published in 2010 or 2019 and published in free text. Subsequently, we had 2 independent reviewers perform risk of bias assessment with the Probus tool, and if they were studies of intervention, we assessed their methodological quality using the Abstract 2 tool. And one reviewer performed reporting quality assessments with Prisma for the main text and Prisma A for the abstracts. So all in all, we included 27 systematic reviews and meta-analyses published in 2010 and 127 studies published in 2019. And as you can see here, most studies in 2010 and 2019 were at high risk of bias. And there was no statistically significant difference between the years in terms of the proportion of studies that were at high or unclear risk of bias. And looking at each subdomain, we can see that the source of bias were mainly in terms of the data collection and data synthesis, with some notable improvement in the use of eligibility criteria. The source of bias from the eligibility criteria used in the systematic review or In terms of methodological quality as assessed by AIMOS 2, again, most studies were at critically low methodological quality, and there was no statistically significant difference between the years, so no improvement. Reassuringly, there was some statistically significant improvement in the reporting quality of systematic reviews and meta-analyses between the years for both the main text and the abstracts. And as you can see here, there were 3.6 more items reported in 2019 with PRISMA, and 1.1 more items presented in 2019 or reported in 2019 with PRISMA. So coming back to our objectives, to answer our primary research question, there was no improvement in the risk of bias or methodological quality of systematic reviews and meta-analyses in dermatology between the years. But in terms of our secondary objective, there was strong evidence of improvement in reporting quality of these studies between the years. And comparing our studies with other studies that have looked at the quality of systematic reviews and meta-analyses in dermatology, they're quite similar, except one study did find there was a lower proportion of systematic reviews with low methodological quality as assessed by AMSR, which is an earlier version of AMSR 2 that we used in our own study. And where do we go from here? Given that systematic reviews and meta-analyses have great utility in terms of clinical practice, we should endeavor to increase their quality of conduct. And one possible solution is to regulate this at the time of submission with quality checks by journals, which can be used or bolstered by the use of automated or machine learning tools. Thank you very much for your attention, and I'd like to
And our last presenter of this session is Yefeng Yang.
Okay. Hello everyone. I'm very excited to be here. In the following 5 minutes, I will take you through some very interesting and some counterintuitive research findings regarding the simple and advanced meta-analysis models. Meta-analysis is such a popular topic, and I think everyone in this conference knows something about it. Generally, it represents a high-level evidence that can inform future research and guide policy making and practice and management. From the perspective of methodology, meta-analysis has many statistical models available. For example, the simplest one is the fixed effect model, which assumes there is a common effect in your population. This is a very strict assumption. Because of this assumption, it is not very often used in the real world. In contrast, the more advanced models like the multi-level model and the multivariate model, they are taking over in many disciplines. This is true in some fields like the animal science and my field, ecology evolution. The data structures are quite complex. They often involve the dependent effect size that are caused by the shared study ID and the shared control. And in more complex sense is the shared species and even shared evolution history can cause the non-independence. So in such a case, we really need to use the advanced models to capture the underlying data generation mechanism. Then you can reduce your type-of error and increase the coverage rate of your confidence interval. So if someone makes a claim like advanced models are more reliable than the simple ones in terms of the parameter estimation and the model inference, I guess most of you will agree with a claim. But is this really true? At least I doubt it. I agree with this claim only if when the data being meta-analyzed is representative enough. However, we know publication bias is widespread in many disciplines, so the data being meta-analyzed are very likely to be selectively reported. So using a non-representative data, actually the most simple model, like the fixed effect model, and even the simple weighted regression can perform better than the complex models. So this sounds a bit counterintuitive, but I will show some evidence. So we did a large-scale empirical test using more than 400 meta-analyses, which include various conditions of publication bias and multiple effect size measures. And we got some interesting results. We see On the x-axis is the effect size from the advanced models, like the multi-level model and the multivariate model, and the y-axis is that from the simple model. But most of the effect size estimates are on the diagonal, which indicate the advanced model always has a larger magnitude of effect size estimates on the condition of publication bound. When there is no publication bound, this systematic trend disappears. So on average, the advanced model will have more than 100% overestimation in the effect size as shown in the two distribution derived from the advanced model and the simple model. Of course, the simple model will underestimate the standard error. This is the point where methodologists they always recommend using the advanced models and to capture the real data structure and reduce the type of error. But this is really not a problem because we can easily to fix this problem by using the robust variance estimation. We see after applying the robust variance estimation, we didn't detect any systematic difference in the standard error between the advanced models and the simple models like the fixed effect model. So we recommend please always use the simple model as a sensitivity analysis in your meta-analysis and report both using a figure like this to show the robustness of your risk finding. Okay, so in a more complex sense, what we really need to sort of is the multiple meta-analysis, which considers all the plausible and reasonable analysis strategies. I mean, to reduce the hidden, to reduce the negative impact from the hidden decisions made by the researchers and transparently report of them. So by doing so, I think we can make a little bit of contribution to reduce the replication process in our academia. So finally, I would like to thank my team in SW, which is led by Smith. Thank you.